So, welcome back to the next lecture. So, this is so we in the last class we were discussing in general the general expression for the velocity gradient tensor Gij, and we saw that any Gij can be written and can be decomposed into a symmetric part and an antisymmetric part. And the symmetric part in turn can be broken down into two parts, the so-called dilation part and the deviator matrix. And each of these have a different significance, a different meaning in terms of the way it gets distorted, the fluid gets distorted because of velocity gradients in the flow. And, so while we were discussing the general part, I mean, in general terms last time, let's take a particular example in that the Gij looks like this matrix. Of course, it's a two-dimensional flow, so there's no third component, that's why. But the point is, let's take this particular example, try to break it down into three parts and have a visualization of the characteristics of this Gij. We are not at the moment worrying how this velocity gradient is produced. We are not discussing boundary conditions as of yet. We are not discussing flow as of yet. But if you are giving a certain flow tensor, what are its properties? What can we say about that flow is what we are discussing. Of course, the forces and other parts will come gradually into the course. And what you see that there is a diagonal part, A and minus A, and you immediately see that the trace is 0, by which you can say that this has no volume element, volume change. So this is del Vx, del x. This is del Vx, del y. This is del Vy, del y, right? So this we are breaking it down and writing it into such a component 0, 0, because we can write that because and then this is the symmetric part, which is the deviator part. And if you add these up, you will get this, right? B plus B is 2B, and there's B and minus B, so here you get 0. All right, and minus A is here, and so on and so forth. So this matrix essentially has the deviator part and the antisymmetric part. And you can, since you know that the trace, the trace is 0, the sum of the diagonal elements is 0, you know that there's no volume change. Hence, we have kept this 0, right? So the dilation part is 0. This has a finite part. So as we discussed, there's no volume change. This of course, what it would do is induce angular displacement so that there's distortion of the fluid element. As we saw last time, there will be a distortion in the fluid element, and this will cause rotation, right? Rotation by this amount of small rotations. So this causes angular deformation, this part, because we know that basically this del Vx del x1 is finite, right? So this along the x direction it will extend, and along the y direction it will contract. This distance will come, and there will be a rotation. So basically, as we discussed last time, if there was a fluid element which was square, after some time it would have become something like this, right? Here basically the x also, the y also has to change. Here the that detail is wrong here, whereas here you see that along the x direction it has indeed changed, right? So that's the effect of that's the effect of this velocity gradient tensor. But if we diagonalize Dij to find out its principal axis. And how would you diagonalize it? Determinant of, so A minus lambda, right? So you do it like this: determinant of Dij, the deviator matrix, minus lambda I equal to 0. And you can just solve this. It's simple. And lambda equal to plus minus a square plus b square. So these are the eigenvalues. And correspondingly, we can find the eigenvectors as well, right? And along those particular axes, once you find these eigenvectors so that it's diagonal, there will be no rotations along those directions, and there will be only stretching and compression along these eigendirections. So what would be the visual, or how would you visualize it? I mean, this is all mathematics, but can you build a picture? I like pictures personally. Uh, okay, so I should have done this, but never mind. Okay. Uh, yeah. So just to again repeat, so the visualization is in the next slide, but just before that, basically the effect of A and minus A would be, the effect of this would be, it would get stretched in this direction. Yeah, but now it's along the eigen direction. So this is not x and y anymore, but x dash and y dash, if you like. Uh, and the amount of stress, the delta x and the delta y, right, would be exactly equal, so that the volume remains unchanged. It would be in such a manner so that the volume remains unchanged. On the other hand, if you had only this component, these are the special cases that we are discussing, when there are only diagonal components. When you had only this component, suppose, what is the picture you should have? Then you have essentially del Vx del y equal to 2b, right? Because all other components are 0, but del Vy del x equal to 0. Now, if you have such a velocity gradient field, I want to impress upon you that it corresponds to a pure shear flow. What is a pure shear flow? Suppose there is a wall here. It is static. It's not moving. So the fluid which is next to this wall will also have zero velocity. It will stick, at least in normal fluid mechanics, macroscopic fluid mechanics, it will stick to the wall, and it will have zero velocity. On the other hand, if this wall is moving with a finite velocity, the fluid will also move, and in steady state there will be a velocity gradient, a steady velocity gradient, which will be set up, and that will be Vx. The velocity in the x direction will vary as a function of y. As you move in this direction as a function of y, the velocity is going to increase, and that's exactly what you are seeing here. Bx equal to 2by, and this is called a plane shear flow to Couette flow, right? So this is the example of Couette flow. So if you had just this corresponds to pure Couette flow along yeah, velocity x increasing in this direction, right? Um, so just to visualize, I mean, such a thing, would correspond to, basically, if you notice, it's so here you have essentially rotation. You have not rotation, it will have essentially stretching. You have angular deformation, actually is the right word. And you can see that basically the corresponding to this Why didn't call? So basically, with the flow field here, it is the y direction is changing the effect of so the effect of these is along x. The velocity of y is changing along y. This is changing, right? And here the rotation is in the opposite direction. I mean, it's moving in the opposite direction. And here, as you go, so this was the flow. But when you take the long term, so these long time, these are the so-called principal axis, and then along these axis, there is pure extension and pure compression. So these are this will be the principal axis, which will of course depend upon the value of and the value of A's and B's, right? So that's what you're going to get. How does one visualize it? This is from the book of Physical Hydrodynamics by the four authors. So what is shown here is there's a printed ink in between a fluid, right? So there's a certain pattern which is lying right in the middle of the fluid, um, and a ball is falling, and as the fluid deforms, you can visualize the deformation of this ink pattern. This is in a plane, and you can see the deformation, and from that you can figure out the velocity field, the velocity gradient tensor, and the deformation and all that. And you, as this series of snapshots show, that basically you can take many pictures, you can have very fast photographs, and thereby you can look at the velocity gradient tensor as a function of time. Um, this is figure 3.5, as you see. The interesting thing is, I mean, while it seems so easy to talk about that there's a pattern created, but remember, this is in the middle of the flow. So what it says is the grid of lines and dots was created in a vertical diametric plane before the ball was dropped. Now, how do you print? So suppose these are small ink particles which are patterned, right? These are patterned. These are ink particles which were patterned in the middle of the fluid. How do you do that, right? Now, I'm not the expert. What I read in the books, in this particular book, there's a small paragraph on it, and I found it extremely interesting. The way they did it was take a half a bowl of fluid and drop ink patterns. I mean, suppose there are holes, and there are holes on which through which these ink fall, and there are metal obstacles which prevents the fall of small ink particles or whatever dust particles, whatever be they, and they are actually dropped on that, and then it lies on the surface of a certain fluid, right? But here you see that this is in the middle of the fluid. The reference to the paper is given, but what they did is, once they had formed this pattern on the surface of a fluid, they took another bowl of fluid and made it stick together so that it became one composite whole. Whole means one liquid. So now you had this pattern which is sandwiched between two liquids, and the two liquids were in some magical way, which I don't know about, joined together. They were joined together, so it became one whole liquid. And uh, now you could visualize uh, this deformation. This picture looks simple, but I think there has been quite some amount of effort gone to visualize this. And I thought that should be, not only you talk about mathematics, but you also talk about how you measure velocity gradients, right? That's extremely important. Okay, so the next we come to the topic of large deformations. Um, so till now we had been talking about small deformations, just in a small time, how much is the deviation, what is the local velocity flow field at short times. Now, if you had large deformation, so that the deformation kept on happening as a function of time, and how do you make sense of that? Not just local tiny, not just dx and delta x and dt, but large deformations. And then let's take this simple matrix Gij, which has only the diagonal parts. And then you can write this as del Vx del x equal to A, and del Vy del y equal to minus A, right? And then you can, of course, integrate it. And this becomes del Vx equal to Ax, and del Vy equal to minus Ay. I mean, you see this. Now this in turn, you write it as del x del t and del y del t and integrate. So what you'll see is what you're seeing from here, that the velocity is changing as as x changes, right? And both in the x and y directions, velocity changes as we move along the flow. At different points in space, the velocity is different. But if you want to look at the deformation, the delta x, then we have to integrate this once again. And then you get essentially putting in the constants of integration, you'll get x equal to x0 minus EAT. So, I mean, if a fluid element initially was at x0, then it's going to, under such a velocity gradient tensor, under such a flow, under a tensor which defines such a flow, x would go like this and y would go like this, right? Uh, yeah, yeah. But if you take the product, xy equal to x0, y0, so the trajectories are branches of a hyperbole. That's the message. These are the initial conditions, right? These are the initial conditions. And so basically, if you took the deviation, the positional deformation, delta x as a function of t, what you would do is x minus x0 from both sides of the equation, and then delta x becomes x0 into e to the power at minus 1. And similarly, delta y as a function of t, the deformation in the y direction becomes y0 into e to the power minus at minus 1, right? So if you have to write it in matrix form, you would write this as delta xt, right? And then these matrices, these are the diagonal terms, right? And for small deformations, of course, you would get e to the power at minus 1. You'll get just 80 for small, for t value is equal to small, where you can ignore the higher order terms of the exponential, right? So things are going to stretch exponentially. What is the message? If you had such a flow, right, and of course you're really looking at it along the principal axis, that's why you have just a and minus a, no terms here, right? Along the principal axis, x is stretching at an exponential rate, and y is being compressed as an exponential rate again. It's basically along this and along this, right? That's what it is. So basically here x and you are basically looking along the principal axis, and this is ideally called, along these axes, it's elongational flow or extensional flow is what it is called. Total volume is conserved, but there's exponential stretching, there is pure extension along one direction, pure compression along uh, other direction, right? So yeah, so the rest we will record in the next module.